Hey, what's up, guys? This is Chung here. Today, let's take a look at this problem, number 272, closest binary search tree value, number 2. So you're given like a non-empty binary search tree. Okay, so remember, it's a binary search tree. So for binary search tree, everything on the left side is smaller than the root node, and everything on the right side, in the right subtree, is greater than the root and the target value. Okay, so and then it asks you to find the k values in the BST that are closest to the target. Okay. For example, this one, the target is 3.714286, and they ask you to find the closest the closest two elements that's in the from the binary search tree. In this case, is 4 and 3. Okay. Uh, so I mean, a common way of doing this is like, since we need to find the closest one, right? So a common way is that we just use a two stack or like a queue, whatever you call it, basically, So for the first stack, we have like we have the numbers that's it's smaller than the target. In this case, it's 1, 2, and 3. Okay, and for the second stack, okay, we uh we store all the numbers that's greater than the target, but we store it in a reverse way. Okay, or we that doesn't really matter. We just store it because here we're gonna store it in the so basically we have 5 and the 4 here. I mean, we can either store it in a reverse way, or it doesn't really matter because as long as when we read it from a different from a reverse direction. So let's say we have these two stacks, right? So now all we need to do is we just need to like select the top case, the top case element among all those two stacks. Yep, pretty straightforward, right? So um, because that will be the uh, basically we're gonna select with these two stacks here. We're gonna try to compare the top two elements, top one element, and we compare it with the absolute value between this value uh, and the target value. We select which one is smaller, and if that is smaller one, and then we just pop these things out, and then we continue comparing with the second one here until until we got case elements here. Cool. So let me try to code these things real quick here. I mean, so to do that, right? I mean, we have to basically we have to loop through. I mean, traverse the tree twice. The first time we need to get uh the smaller number, and the second time we're gonna get the bigger number. Okay. So let's see. We have a smaller. Okay, and here. And then we have a bigger of this. Okay, so we need to do a DFS basically, right? So uh, DFS DFS smaller. Okay, sorry, smaller, and then we have node here. If not root, right? We simply return none here. Okay, and then we do a DFS node left. Okay, and then with the current one. Since we're going to the very left first because that's gonna be our smallest number here. Okay, and for the smallest number, we're gonna insert it into Basically if the root the node dot value it's is equals smaller than the target, and then we just add it. We just smaller dot append to with the node dot value. Okay, so we're doing like a smaller here, equal smaller or equal here because if the target is the if the target is this happens to be the same as one of the node here, I mean we're gonna put that node into the smaller but stack here. So which means when we DFS the bigger ones, we're going to use the greater, not the equal, because we don't want to duplicate that same node into two stack here. Now, this is like df right, okay? Now I can just simply copy these things here, right? So that's for the smaller, and now we have a bigger here. Bigger, okay, same thing here, but instead I'm going to do this, right? I mean, smaller, sorry, bigger, okay. Okay, so I mean here, I mean we can store it, we can append to the end, but if we append to the end, we have to it's fine. Yeah, I think it's fine. We can just append to the end. So because we are also going to the left. The left one is basically the smallest one on the left, that's on the bottom. So it's 4 and 5. Uh, let's do that. Let's just keep them same. But remember, when we read the value from the bigger ones, we need to read from the first one. Okay. So and yeah, so now just do a DFS smaller and with the root. Okay, and then DFS bigger with the root. Okay. Now let's populate our answer here, right? So the answer is a list, and we have while k is greater than 0. Okay. Uh, Basically, if if not smaller, right? If smaller is empty, then we simply do answer dot append from the bigger one. Okay, so the bigger one is like pop 0. Right? Remember, we are popping from the left. Okay, that's why we do a pop 0. Uh, Else if not bigger. Okay, if it's not bigger, the same thing. Append smaller dot pop. For smaller, we can pop from the top, right? Because it's storing like this. 1, 2, 3. Okay. Uh, Else if both of them have a values, then we just need to compare, right? If ABS smaller dot -1, right? That's the minus target is smaller, okay, smaller than ABS of the bigger one is the 0, it's the first one, right? Remember that, okay, minus target. So this thing it means that the smaller one, the top one, the smaller one is closer to the target. So we do a dot append smaller dot pop, okay. Else in the end we just do the other one. We just do this bigger one, okay. Yeah, and then in the end we simply return the answer here. Cool. Yeah, I think this should just work. Let's try to run the code. df sorry, dfs here. Bigger, bigger, bigger. Okay. Sorry. Note value. Oh, yeah. Val here, not value. Uh, okay. Some typos here. Uh, pen. Okay. A few more typos here. Hmm. Append bigger append node 41. Pop from empty list. If not smaller. Huh, this is weird. Mm, yeah, this is. Yeah, because it's weird. It says the k is smaller. It says k is smaller than the total nodes here. So if smaller is not is empty, and then I append the bigger ones. Bigger dot pop 0. Okay, let me check that. Oh, I know. So uh, I forgot to decrease the k here. Of course. Run the code. All right, cool. So this time it works. Let's try to submit it. Yeah, so it passed. All right. I mean, so th this one is pretty, I think it's straightforward, right? I mean, the time complexity, right? I mean, the DFS and the DF is bigger and smaller. It's just like two, O of n here. This is O of n here because we are like basically we're storing we're traversing everything, right, from the root node here, from the tree here, and here it's just like a k here, right? So that's the k. So basically that's gonna be a O of n plus O of k here. Okay. So maybe a few thoughts on this follow-up here. And as you guys can see, we have a ON plus OK time complexity here. And the follow-up is assuming that the BST is balanced. Could you solve it in less than ON runtime? So which means that can you solve it by not traversing the whole tree here? So what I'm thinking is that, since it's balanced, uh, we still gonna keep like smaller and uh, bigger like a node here, a stack here, but instead of traversing everything, we're just traversing from the top, you know, from the top to here, since it's a balanced, right? Balanced is like this. I mean, balance is not like completely same. Maybe the left and right one, the height is not bigger. The height difference is not bigger. It's at most one. Okay. So I'm thinking if that's the case, we can traverse from top down here, and if this one is it's smaller than target, we just put into the smaller one. And if it's bigger one, and then the bigger one, right? And then we go to the left. And then if this one's uh sorry, let me think here. So I mean, if the current node is smaller than the target, and then we go to right, and then we compare with this one if it's smaller or bigger. So basically, we always go to the opposite directions, and after that, we'll have like a smaller and bigger ones that are storing part of our answers here, right? And then we can with this, and then the time to get to populate the smaller and the bigger one will be like the log n, right? Uh, log n time, and then later on here in the while loop here, we just need to basically we have an initial state of our case value here, and then we're trying to expand. Basically, we're trying to expand that's the numbers. We're trying to expand that this list here, right? I mean, if this list, if the smaller and bigger one does not fit, is even smaller than k, we'll just try to expand that. But to do that, in order to store the value here, we need to store the node itself, so that later on, when when we have used one of the values here, we can just uh, we can just get another value by doing by getting the predecessor or the successor from the current node. So in that case, I mean the time complexity will be a log n plus k. Sorry, log n plus k here. I mean I didn't implement that one, but if you guys are interested, you can just try to implement that by yourself. Okay, cool guys. I think that's it for this problem. Yeah, thank you so much for watching the videos, guys. Stay tuned. See you guys soon. Bye bye.